Good morning.
Good morning. How are you?
I'm okay.
Excellent. Good to hear.
Yeah.
So, should we get started? Do we have any questions before we get started? Okay. So, gentle reminder that there are 3 labs that are going to be due on Sunday. So, that's the factors affecting reaction rates, which is not really a lab report, it's just some comments on what you observed. And that all uses information that's in D2L under assignments. And then there are 2 Alex labs and 2 post labs for those. Now, if you haven't done those yet, please be aware that the expectation is that you will use notes when you do those post labs. So it is expected that you will write down what you did during the lab and then use those notes to take the post lab. These are complicated labs. You're doing a lot of math. So the expectation is not that you've memorized it between doing the lab and doing the post lab. The expectation is that you can look at your notes and use those notes to be able to answer the questions on the post lab. Does that make sense?
Yes.
Yep.
Okay. So what I typically do, if you've seen the little paper clip that's down at the bottom in the lab notebook, it gives you instructions for how to do those calculations. I actually screenshot that and use those when I'm taking those quizzes. So if you have any questions about that, let me know. You do have 2 attempts, and because it's the first set, if you guys need some additional help with that, just contact me, let me know about that, and we'll see what we can do to get you through it. Okay. The goal is not to have the post labs be what destroys your grade. That's not the goal. It's to test to see if you learned anything during the laboratory. Now, the lowest post lab will get dropped for this term, so you keep all the labs, but you'll drop the lowest post lab. Okay? All right. So we've talked about reaction rates, how fast a reaction happens. We've talked about some conditions that we can manipulate to make those rates change, like things like concentration, temperature, surface area, adding a catalyst. Those are all things that can change how fast that rate will happen. Okay. And then we talked about equilibria, which describes where in this reaction, that whether it be the forward or the reverse reaction, does that lie? So how much product do we have versus how much reactant do we have once it reaches equilibrium? They're not all the same, all of that good stuff. Okay. Now we're going to go back and talk a little bit, do some review about acids and bases, because unlike what we did last term, where we only talked about strong acids, where we knew exactly what their concentration was based on the fact that they were strong, we're going to have to set up so that we can do math with the weak acids and the weak bases to figure out what their concentrations are going to be based on their equilibrium constants. Okay, so that's where we're headed with all of this. Once we've talked about the equilibrium stuff related to this and done a lot of the math there, then we'll start talking about the titrations that we do with weak acids and weak bases. Now, I know in 110 you did 1 weak acid titration, and you looked at that from a purely, qualitative perspective, not quantitative, qualitative. This time we're going to do a little more in terms of looking at what are those numbers, since we'll be able to look at how now we have enough information to be able to calculate that. Okay? Well, that's where we're headed. What we're going to be talking about is some review from 110 about acids and bases today. So that's basically what today is going to encompass, is what are acids and bases? What are the definitions by which we talk about them? What are things that go with that, i.e. pH, and how we measure pH? What the pH is, what the pOH is, what's the H3O plus, the OH minus. Okay, we'll get back to the fun box. And then we'll start talking about the strengths of acids and bases, not only in terms of strong versus weak, but also comparing those weak ones. Okay? All right. So the general generic descriptions that we talked about in 110. Acids are sour in taste. They change the color of plant dyes. They react with some metals to make hydrogen gas. They react with carbonates and bicarbonates to make carbon dioxide. And they do conduct electricity. Bases are bitter in taste. They feel slippery like soap. And again, that's because the initial soaps were made out of NaOH, which is a base. Change colors of plant dyes. So I don't know why that's useful because both acids and bases do it. And they, in aqueous solutions, will conduct electricity. And that's based on the presence of those ions. We talk about arsenous acids, which is the first thing that we talked about. We always talked about acids being H plus donors. Okay. And then when we talk about the bases in the arsenous definition, it's an OH minus donor. Okay, so that was our first definition. So again, we had our arsenous acids. Donate H plus and arsenous bases. And I think I'm spelling that wrong, but that's okay. Spelling is not important, at least not on your test. Will donate an OH minus. But of course, when we discovered that NH3 can act like a base, it doesn't donate an OH minus when it does that. And so we had to expand our definitions. So that's where we get this definition down here for the Bronsted-Lowry acids and bases. Okay, so Bronsted and Lowry both came up with this idea around the same time. And they said that acids donate H+, so same definition that we had before, but the bases accept an H+. Okay, so now we have an expanded definition for those bases. So anything that can accept a proton can act as a base, right? So those are those two definitions. Now, when we talk about neutralization, we're talking about the complete reaction of equal moles of acid and base to form a salt and water. And what I mean by a salt is an ionic compound. So could be something like sodium chloride, could be anything, as long as we've got an ionic compound and water that comes out as of that reaction. And that's always what we see. We have to pay attention to the reaction stoichiometry when we do that. Now, the majority of the time, it's a one-to-one relationship. Okay, that's almost always what we use. But we do have situations where we're talking about acids like H2SO4, which has 2 protons, or H3PO4, which has 3. And so the stoichiometry for those are going to be different. Okay. The other thing that we'll see occasionally is we'll have an OH that's like BaOH2, and so it has 2 OH groups on it, and so we'll have to balance for the 2 OHs that are there. Okay, so that's important. Now again, we can get formation of gases, carbonates, bicarbonates, sulfates, sulfides, all of that stuff produce gases. And what really happens is we form a like Na2CO3, which is sodium carbonate, and then that decomposes to give us CO2. So that is something that we see from that. The expectation is not that you can balance an equation like that. That was something I was tortured with. I don't think it's necessary to make you do that. Okay. So questions about our reviews, what we talked about in terms of acids and bases previously. Okay. So you'll be expected to know the definitions. So you would be expected to be able to tell me, is this an arsenous acid? Is this a Bronsted-Lowry acid? Is this a Lewis acid? Lewis base. If you took 110 here, you remember that there was a question on the final that asked you to define which ones they were. So that is something that we do have the expectation that you can do that. So we'll talk a lot about how we can identify those things. And then we're going to talk about Lewis acids and bases in just a minute. We also have a couple of terms, amphoteric, meaning they can act as both an acid and a base. H2O is an excellent example of this because H2O can react with another H2O to give me an H3O plus and an OH minus. And so one of these has acted as an acid, donated a proton to the other one, which then acted as a base to give us this H3O plus and the OH minus. Okay, so it's acting as both an acid and a base in that case. When we talk about conjugates, we're always like talking about an acid and its conjugate base, or base and its conjugate acid. And the only difference between the two of them is one proton. Examples: H2O and OH minus. This would be my acid, the H2O. This is my base, the OH minus. H2O and H3O plus. Okay, in this case, this is the acid, this is the base. Because again, I have one more proton here than I do here. Okay, so that's how I know that that's the acid. All right. NH3 and NH4 plus. In this case, this is the base. I know that NH3 acts as a base. It can pick up a proton to become NH4 plus, which then is the conjugate acid. Okay, so you need to be able to identify those conjugates. We'll talk about that quite a bit. There'll be questions about what is the conjugate of this, what is the conjugate of that. When we talk about binary, we just mean that the only thing I have is like an H and some anion. We generically talk about that in terms of HA, which can donate H plus, and then we get the A minus, which is just an anion. That A could be Cl, it could be some other ones, Br, those kinds of things. So HF also falls into this category, although that is a weak acid, is the only halogen acid that is weak. And of course, when we talk about this H plus, it's always assumed it is the same as H3O plus. So the H plus, when it gets into water, always gets picked up by an H2O. It does not exist on its own. We just are lazy and don't write them. The other thing is we don't need to have the H2O in the equilibrium constant. So if we leave it out, then we don't have to remember to leave it out when we write the K. So questions about that? Okay. So again, when we talked about our heinous acids, the acid, when dissolved in water, produces H plus and therefore increases the H3O plus. Okay. The base, when dissolved in water, produces OH minus and therefore lowers the H3O plus, increases the OH, therefore lowers the H3O plus. And again, that's based on the equilibrium for water. So when we talk about water, which acts as its own acid and base, we have this situation here, which gives me the H3O plus the OH minus. The K for that is H3O plus times OH minus. Because those H2Os are both liquids, so they won't appear in that. So this is the K that we have. And so if this one goes up, this has to go down. Now, at room temperature, and only at room temperature, Kw is equal to 1.00 times 10 to the minus 14th. If we change that temperature, that will change the value of K. That therefore changes the value at equilibrium of both H3O plus and OH minus, which means that our pH scale will shift if we are not at room temperature. Okay. Our neutral point always exists where we have equal amounts of H3O plus and OH minus. But if the amount of those two things has shifted, then the natural log, or taking the negative log of that H3O plus, is no longer going to give us 7. Okay, so remember that that is the case. You may get asked a question about that. So there's that portion of it. Now, when we talk about the Bronsted-Lowry, I list that as B/L because it takes a lot less time to write. Our acid is still an H plus donor. Our base is an H plus acceptor. And then we get into our Lewis acids and bases. And the definitions here are a bit different. We're no longer talking about H plus in really any way at all. We're talking about electron pair acceptors versus electron pair donors. Now, the base part is, in my mind, was always fairly easy for me to understand. NH3, when I drew its Lewis structure, 3 protons down like this, and then a lone pair up here, right? And that lone pair gives it the ability to act as a base. So I can take that lone pair and donate it to something else. Okay. The way that I normally talk about this when I talk in 110 is to show BF3. Move my bond. Sorry, that's a bad bond. Which looks like this. And each F is surrounded by 6 electrons. But because boron only has 3 electrons to donate to this, this is the structure that we come up with. It's electron deficient. And that's one of the reasons that I like to talk about it, because it doesn't fulfill the octet rule for boron. It can't. Boron cannot make a double bond with fluorine because there's no availability of d orbitals for it to do so. So this is the best structure that we came up with, and it's electron deficient. So if we have this pair of electrons here, they could be donated here, and therefore NH3 is acting as a Lewis base by donating that pair, and BF3 is acting as a Lewis acid by accepting it. Okay? So I liked this because it gave me a concrete way to think about it. It wasn't just this abstract, oh, we're donating, a pair of electrons. This is typically the kind of thing that you look at in organic chemistry. We don't talk about it that much when we talk about inorganic chemistry, which is typically what we deal with in 110. But if you're going to have to take, the 211, 212 series, it's important that you understand how those electrons move. So this is where we start talking about things like that. Now, some materials that are Lewis acids are not Bronsted-Lowry acids. Okay, so there's no donation, like with this BF3 here, there's no donation of proton here. Some materials that are Lewis bases are not Bronsted-Lowry bases. Okay, so there's no accepting of protons here. But it is possible for them to be defined as acids by more than one of these things. Okay, a lot of times you'll see that there are Arrhenius and Bronsted-Lowry acids. I mean, if they're one, then they're the other by definition. And the base portion may or may not be true. But sometimes they are also Lewis acids and Lewis bases. So keep that in mind when you're being asked to identify these things, because they may fall into more than one of those categories. Okay? Questions about those? All right. So I like charts. So for me, this was easier to look at and to try and pull all of that information together. So my Arrhenius acids donate protons. The H plus will increase, the OH minus will decrease. It's not necessarily by definition another type of acid. When we talk about Bronsted-Lowry acids, we still have that H plus donation. It increases the H3O plus, decreases the OH minus, and by definition is the same as an Arrhenius. Okay, so they're both those. When we talk about the the Arrhenius bases, that's an OH minus donor. It decreases the H plus and increases the OH minus. It is not by definition anything else. Our Bronsted-Lowry bases accept an H plus through a non-bonding pair of electrons typically, and the H plus will therefore decrease, and the OH minus will then have to increase. That's just what has to happen. When we talk about our Lewis acids and bases, we don't necessarily change that H plus OH minus ratio. Okay, in a situation like NH3 plus BF3, that doesn't happen. So that may or may not be a situation that we're talking about with that. It may not change our pH scale because they aren't, proton donors, proton acceptors, so it may not. Okay. And they aren't by definition anything else. Okay.
I thought you said that the Bronsted-Lowry acids and bases are Lewis bases, acids and bases by definition.
I don't think I did. I shouldn't have.
Did it not say it on the last slide? I'm confused. Sorry.
I'm flipping back. Yeah.
At the bottom, it says all Bronsted-Lowry acids are
This is,
also base or Lewis acids.
that shouldn't say that. That should say arginines. And actually, this is not true at all. I'll fix that. But does that, so my slide is wrong. That is true.
Okay, thank you.
But yeah, the Bronsted-Lowry acids are arginous acids. Bronsted-Lowry bases may or may not be arginous bases. So I apologize for that. That's my fault. And I'll fix that. Hopefully I'll remember this time. Okay. So cool with that. So, and I've said most of this already. Lewis acids and bases have nothing to do with the H plus or the OH minus production or proton donor acceptor behavior. Lewis definitions: Lewis acid accepts a pair of electrons and the Lewis base donates. Lewis structure, and again, this example that I gave here, I actually already did this. So my Lewis base, my Lewis acid, and they can interact because of the donation of this pair of electrons. Okay. Now, something that you should be able to do at this point is to fill out a table like this. Okay. What this indicates is that I have a molecule. I want to know if it's a strong or weak acid or base, depending on which it is. If it is a proton donor or an OH minus donor, or that kind of thing. Does it fit the arginous acid or base definition, the Bronsted-Lowry acid or base definition, and the Lewis acid or base definition? Okay. And it says, if you're given a 0.1 molar solution of each species, do you know what the concentration of each ion would be? And if so, what would it be? So I'm going to walk through one of these so you make sure that you understand what I'm talking about, and then I'll probably just walk through the rest of them as well. So when we talk about HF, is HF a strong acid or a weak acid? It's a weak.
It's a weak
And it's
acid.
a weak acid.
Yeah, weak.
Yeah. And it's weak acid because it has a really short little bond, so it's very hard for it to come apart. Now, when it does come apart, I do get an H plus that comes into solution. And therefore, by definition, it's an arginous acid. It's a Bronsted-Lowry acid, but it does not fall into either of these categories by definition. When I talk about HCl, it is a strong acid. And because it's a strong acid, I know what the concentration of all of these are, and that's 0.1 mole. So the expectation is that if HCl goes into solution, I only get H plus and Cl minus out of this. So there is no HCl left. So anything that was here, if this was 0.1 molar, has now been converted. And so both of these will be 0.1 molar because they both came from here. And so when it breaks down, I get one of each of those. Okay. So that's what we're looking at in terms of knowing what those concentrations are. It is also an H plus donor, and therefore fits my arginous definition and my Bronsted-Lowry definition, but not necessarily anything in Lewis. Okay. When we talk about H2SO4, the interesting thing with H2SO4 that we need to talk about now is it's listed as a strong acid. That is very true. But the funny thing is, it donates those two protons in a two-step process. Okay? So what happens is that I have an H2SO4, which gives up a proton to become HSO4 minus. That HSO4 minus, giving me an H plus the SO4 2 minus, this is not strong. That's a weak acid. Okay, so whether it's a strong or weak, well, we normally define that by the first proton, and so we would mark it as a strong acid. And what I know at this point is that I will get at least 0.1 molar H plus from that. It should be larger than that, but I don't know how much larger. Okay, so I know that this one is greater than 0.1 molar, but that's all I know at this point. Okay, and that's because that first donation is strong and the second one is not. It is an H plus donor, and so it is an Arrhenius acid, and it is a Bronsted-Lowry acid. And I don't necessarily know anything about that Lewis part. Cool with that. Now, just so you know, I will never ask you what the concentration of H2SO4 is, because that's a two-step process and it's a lot of math, so I won't ask you about that. And
So
when we talk,
did you
go
say
ahead.
the concentration of H2SO4, it would be 0.1 molar for each part just because it breaks down that way?
So no, I get complete dissociation of the first proton, yes,
Okay.
and so I know it's at least 0.1 molar, but the second part is not a complete dissociation. So I know it's greater than 0.1 molar, but that's all I know.
Okay. So that's how you would put it, just greater than 0.1 molar.
I'm not going to ask you about that. So this, but that's, yes, that's what I would put, is because I know it's greater than 0.1.
Okay. Thank you.
So, yep. Now, on our HNO3, when that comes apart, I get an H plus and an NO3 minus, so it is a proton donor. HNO3 is in my list of strong acids, so I know that that concentration will be 0.1 molar. Okay. Is it an Arrhenius acid? You bet, because it donated a proton. Is it an Bronsted-Lowry acid? Yeah, because it donated a proton. I don't know anything about the Lewis properties. All right. Now, let's talk about MgOH2. Now, MgOH2, when I look on my periodic table, or not the periodic table, the exam handouts. Let me pull those up. Because the acids are easier. So if I flip through these exam handouts that you guys will get, there is a list of strong acids and strong bases on this. And you're told to consider anything that's on this list as strong, anything that's not as weak. So HNO3 was here, H2SO4 was here, HCl is here, HF was not. When I look over on this side, I don't see that MgOH2 is over here. Okay, so what that tells me is that I am supposed to think that it is a weak base. Okay, so I will get some dissociation of the OH, but I don't know how much. And so that means it's an Arrhenius base. It can act as an Arrhenius or a Bronsted-Lowry base when it accepts a proton, but and yeah, I would indicate that, well, no, I would indicate it that it's an acid by definition. It can do it through action afterward, but we're not going to talk about that. We're just talking about, based on the definition, is it a Bronsted-Lowry base? And I would say no, because it's not automatically accepting a proton. Okay, same is true with the Lewis. So it can act that way when it's reacting with something else, but on its own, I wouldn't think about it that way. All right? So cool with that.
Kind of. It's just, can you Can you do like another example? Just like one more.
I was going to do the rest of them.
Oh, okay, that's good.
Yeah, I figured I should walk you through all of these because it'll make it easier. So, when we talk about BaOH2, that's here in the list of strongs, right? So, since it's in that list of strongs, I have to treat it as if it's a strong base. So, this is a strong base. It is an OH minus donor. I'll come back to the concentration. So it acts as an Arrhenius base because it donates that OH minus. But its ability to pick up a proton is a secondary part of that. So it doesn't, by definition, fit the Bronsted-Lowry or the Lewis. Okay. It can act that way when it reacts with something else, but unless it's in that reaction, it wouldn't fit that definition. Now, when we talk about concentration for BaOH2, unlike what we talked about for H2SO4, this is a complete dissociation. Okay, so every time I take a BaOH2 and I put that into solution, I get a Ba2 plus 2 OH minus. That is a one-step process. And so that means because I get 2 OH minus out of it, the concentration here will be 0.2 molar. And that's based on the stoichiometry for that particular compound. Okay? Those are things we have to watch out for because those can be problematic in terms of balancing equations. So question about that one.
I'm sorry, why does it work with Ba but not with magnesium per se?
Well, magnesium is actually not that soluble, so
Okay.
it's not a strong acid or strong base. So within our list, it does not come up as a strong. That's how I made that definition. When I pull, hold on, give me a second. When I pull this back up, it is not on this list. And therefore I don't know what that concentration is. And that's because it has limited solubility. So, and yes, that is a reminder. Go and check and see if it's strong and then determine what happens. Because that's really how you should be doing. Now, NaOH, I know, is a strong base. Okay, I don't have to check the list. If I check the list, I will see it's that it's on. It is definitely an OH minus donor. And therefore, it will be an Arrhenius definition of a base. Not necessarily Bronsted-Lowry, not necessarily Lewis. Okay? Because it's a strong base, it completely dissociates. Therefore, I end up with a 0.1 molar solution there. Okay? Cool with that.
Could you go over again why the BaOH was 0.2 molars?
Yeah, it's because when I dissociate that, the BaOH2 goes to a Ba2 plus 2 OH minus. If this is 0.1 molar, then this is 0.1 molar. But this, because there's two of them, will be 0.2 molar. It's because of the stoichiometry.
Oh, okay.
Yep. So cool with that. Now, looking at this list, like I said, NaOH is here. NH3 is not. NH3 is a weak base. And so if it's a weak base, I need to mark that as a weak base. Why did you do that? Thank you. So it is a weak base. It is not an OH minus donor, but it generates OH minus in solution. So let me walk through that a little bit. We take that NH3 and I add it to H2O. And what happens is that the NH3 picks up a proton and becomes NH4 plus and leaves an OH minus. So I do end up with OH minus in solution, and that therefore changes my pH. And that was really what I was looking at for this, was do I generate H plus or OH minus based on these behaviors? It is not an
I have a
alkenes.
question.
Yes.
Sorry.
No, you're fine.
I guess okay, so I'm just getting confused on so whenever we're like checking it, right? Like the like the barium or whatever,
Mhm.
and we
Yeah.
check it and it's why don't we also add like the H2O to that? And it's like why'd you just add it to the NH?
Because the other things don't require anything else to get to a state where it's acting as an acid or a base. HF comes apart by its own. HCl comes apart by its own. H2SO4 comes apart by its own. All of those things
Oh,
happen
is
in
that
water.
because it's like a polyatomic thing? Is that because
It's
it's
because
polyatomic?
it's because they're ionic. That's correct.
Yeah.
So as
Okay.
soon as they go into
Thank you.
solution, they will dissociate. Correct. Yeah. NH3 will not come apart, but it does pick up that proton from water. So that's why. Now, because of that, it is not an Arrhenius base because it does not donate OH minus, and that's the definition that's there. Okay, so it doesn't fit that definition. But a Bronsted-Lowry says that it will pick up that base, will pick up a proton from something else. And so it does fit the definition of a Bronsted-Lowry base. That's true. It also fits the definition of a Lewis base because the reason that it's doing what it's doing is because of its lone pair. So because it's donating that lone pair to the water and pulling that thing off, then it's acting as a Lewis base. Okay, so it does act as both a Bronsted-Lowry and a Lewis base. Okay, so that's the kind of thing I want you to be able to think about, is looking at the reaction that you're looking at. How is it behaving? Is it doing this? Does it fit the definition as it's been given? And so you have to remember what those definitions are, because I mean, they could be really confusing, because it's like, okay, the acids seem really easy to me because it's always proton donation, accept something. That's easy. When we get to those bases, though, it's like, well, did it generate the OH minus on its own? Did it generate the OH minus some other way, like NH3 does? Or did it use its lone pair to act with something else to do something? Okay. So it's in my mind, the bases have always been a little more confusing because the definitions are a little harder to see. So I hope that helps. My goal in showing you this particular list was to show you the behaviors that you would probably need to be aware of. Okay.
It did help. I think that's just something I'm gonna have to practice on my own too.
Unfortunately, yes, this was a flashcard situation for me. And while I understand that some instructors make flashcards for their students, I find that if I make the flashcards, it doesn't help.
Yeah.
So part
I
of the
mean,
art of learning it is making them.
yeah. So if I do the flashcards, should I just like put like each one on and then like see? Okay, yeah, never mind. Sorry, I'm talking to myself.
Oh, that's all right. We can talk about it later if you want. So questions on our, sort of what these definitions are, the ways that you might see that as a question, any of the things that we've been talking about so far.
Yeah, how would you like, so is it gonna be on the test like kind of like that where it's like a table?
Kind of like that, yes. That's not all
What
of
do you
it,
mean
but yes.
kind of?
Well, there's another part we'll get
Okay.
to in a bit. So, and
Ah,
I've
okay.
yeah, because once we start to learn how to calculate what the concentrations of the weak acids and weak bases are, then I can ask you, what are those concentrations for all of those species? because we can do it for anything that's strong right now, but we can't do it for anything that's weak because we don't know how to do it. But we're going to learn.
So on our exam handout, we have a list of like whether or not, well, it's a list of like strong acids and bases. So that's how we'll know like if one is strong or weak
Yes.
because
So
they are on the exam handout.
Yes, this is the exam handouts. This is actually page 8, and this is the list that you get. Now, there are also pieces of information on this that will help you guys, because back here there are lists of weak acids and weak bases that are here. The thing is, though, just because it's not in the list of weak acids or weak bases does not mean that it's strong. So that's why I present the strong list, because if it's not on the strong list, it's weak, whether or not it's here. So, okay. Yeah. Yeah. I would familiarize yourself with the information that's on those exam handouts. It's supposed to be consistent with what is in ALEX. So you should, in theory, be able to use that when you're working in ALEX to try and see where things are, where you will find them, and get used to working with that document, because it'll make your test a lot easier. It is long, it is like 14 pages. So, okay. All right. And one of the things I mentioned that we were going to talk about was conjugate acid-base pairs. So you'd be asked to identify the conjugate. So in order for us to do that, we have to have a reaction. We have to be able to identify what in that reaction is acting as an acid, what is acting as a base. So if I look at the reaction right here, HNO2 is an acid. It is defined as an acid. And that means that if this is my acid, this must be my base. When it donates this proton, which it does because it's an acid, then my H3O plus forms, okay, meaning that this picked it up, so it is acting as a base. Once it's done that, it makes an NO2 minus, which is the conjugate base of that acid. Notice that I've lost a proton between these two. So because it's one proton different, that makes it a conjugate acid-base pair. So we would talk about our acid and its conjugate base. Okay, so I can identify that. When we talk about our base, which is here, it picks up a proton from HNO2 and therefore becomes its conjugate acid, which is H3O plus. So my base is the H2O, its conjugate acid is the H3O plus. When I'm looking at those pairs, we're always talking about the difference between them being one proton. The acid is the one that has the extra proton. Okay, so it doesn't matter which side it's on, whether it's the acid side or the conjugate acid side. So either way, it's always the one that has the extra proton. Does that make sense?
Sorry, can you explain that last one again?
So the fact that they're always related by one proton and the acid always has an extra proton. Okay, so if we're looking at these guys down here, I've got my HNO2 and my NO2 minus. The one that has an extra proton is this one right here. So that proton means that this is the acid, this is the base, because I've lost that proton to get to the base. When we talk about the other pair.
Oh, wait. Okay. Yeah.
Okay.
It's
yeah.
like
so
adding because since the H3. Yeah. Okay.
Right. Correct. Yeah. So when we talk about this pair, the H2O, we add that proton. This is the acid, the conjugate acid, and this is the base because this is the one that has the extra proton.
Oh, okay. Okay. Yeah. Okay. Thank you.
Yeah. Yes. So and don't worry, trust me, that tripped me up a lot. So this is why I harp on it so much, because it bugged the crap out of me when I was a student. So we always, again, are looking for difference of one proton. If it's more than one proton, that is not a conjugate acid-base pair. So you might get a multiple choice question where you see a bunch of pairs and get asked which is the correct conjugate acid-base pair. That's what you're looking for, is the difference of one proton between the two species. Okay. So here, I have a list of things. And what I want us to think about is, what would the conjugate of that look like? So now I've not told you whether it's an acid or a base. I just want you to identify what is the conjugate of that. Now I'm going to walk through each one of these so that you can see what these answers are. Okay? And hear the logic that I have in getting from one to the other. All right. So I see HI here. I know that it has an H on it, and therefore its conjugate should just be the I minus. So I took off an H plus, it therefore has to be a negative, so I minus. I have an H plus here. The conjugate of that has to pick up an anion of some kind. Now what that anion is does not matter. So I could call this an HA, I could call this an HF, I could call this an HI. It doesn't matter. You're usually given some kind of context for that. So, but if you're just asked to randomly tell me, pick some anion. Does not matter what that anion is, as long as it's a -1, because I have an H plus here. Okay. Now I have an H2PO4 minus. There are two things that I could do with this. It has a proton, right? So I could take off a proton, and then I would end up with an HPO4 2 minus. That's one way I could go. So this would be my acid, and this would be my base. But this right here also has a negative charge on it. So I could put another proton on it. And that would then be H3PO4. So this would be my base, and this would be my acid. In the case that you're given something like that where it can act both ways, it's up to you which way you decide to do it. Unless it says, give me the acid of this. In which case, the only correct answer for the acid of that is the H3PO4. If I say, give me the base for that, then you would have to go HPO4 2 minus, taking that proton off. Okay. But in the case where you've got something that could be an acid or a base, so it's amphoteric, then you can choose either one. Okay. I have HClO4 here. This has a proton on it. I need to take that off. So ClO4 minus is the conjugate base of that acid. Okay.
So,
Now,
is it why? So why wouldn't we like add the H again? So is it because it doesn't have anything? It doesn't have an ion.
yeah, so that's obviously, we've lost something from that. And so the conjugate of it has to add that back. So whatever that was.
Oh,
Because we already got the H plus. So if I add another H plus to it, then that's turning an acid into an acid. And I don't want to do that. I want to turn, since I've got that H plus, I need to turn it into a neutral compound. So ways that I would know I need to do something like that is, if I see an H plus, that's always where I'm going to add some anion to it. The other places I would see something like that, the flip side of it, is where I see something that has a negative charge on it, because that's an anion that then there needs an acid, a proton added to it. Does that help?
yes, it does. Thank you.
So now let's talk about our OHs. So I have to think a little bit about these. It's not as obvious from where I'm at. So I have to think about the fact that this becomes Be2 plus 2OH minus, right? And the only thing in here that could be an acid or a base is this OH minus. And so if this is the base that I have, and I want the conjugate of it, I need to add a proton to it. So then it would be my base, the OH minus, pair that I'm looking at. Because all I have is the OH minus, which can only act as a base. I mean, the B can do stuff, but not in an acid-base sense. Okay. When I talk about my CaOH2, I end up with Ca2 plus 2OH minus, and I end up in the exact same scenario that I just had. Because it's that OH minus that I can then add the proton to get that pair.
So we just like ignore like, you know, like beryllium and calcium and just focus on the OH.
Well, so remember when we talked about aqueous solutions and we had the spectator ions? Those are spectators.
Yes.
So because they're
Oh,
spectators, we don't need them.
okay.
Yeah. So yeah, they're just there because I need something that has the same charge to be able to put that into solution. So that's all. When we talk about our RBOH, break that down. I get an RB plus and an OH minus. The OH minus is my base, so therefore I add a proton to that. And get H2O yet again. So that's a fairly common thing for us to see. If we've got those OHs, that's what we'll see out of that. So cool. That was fun. Now we get to some stuff that might look a little bit different. When I talk about CH3 and H2, I can tell from the way that this is written that this is not an acid. Now, why do I say that? This thing has CH3 and H2, and if it had a proton that it could donate, when I'm talking about this, that proton would be either be out in the front, and then it would be HC2 and H2, or we'd see it as like CH3 and H2H. Okay, something along those lines. The way that it's written is meant to emphasize whether it's an acid or a base. Okay? So the way that this is written, I know that it's not an acid. Because it has an ammonia on it, that NH component at the end, I know that that N has a lone pair. And so it can act as a base. Okay. If it can act as a base, then if it's acting as a base, then its conjugate acid will have an additional proton. So that would be a CH3 NH3 plus. So when you see a compound that has an NH in it, any kind of N thing that goes with it, understand that that can act as a base. And so either it's got a charge on it and it already has picked up a proton, or it can pick up a proton and get a charge. So that's a case where it was neutral and I picked up a proton and became a charged species. So again, this is my base right here. This is my acid right here because it has an additional proton. When I look at this one, it already has a charge. So I know that it's already picked up a proton. And so if I take that proton off, that's a C6H5N. And so this case, this is my acid here, and this is my base here. So you're always looking for the presence of that H plus. So if an H plus has been added, you should end up with an H and a positive somewhere. And if it's been taken off of it, you should end up with a negative charge somewhere. Okay. Cool with that. That is how most of our
So for that one, was
yes.
it originally an acid and we were matching the conjugate base? Is that what that was?
Yeah, this is our, well, technically this is a conjugate base, and this is the acid, conjugate acid, and this is the actual base form. But because we were given this, we would then say that this is the acid, and this is the conjugate base.
Okay.
So the conjugate just means that we've made the change. If you were to look at this up in a table, you would find it in a base table this way. Does that make sense? Okay. Now, some more practice based on everything that we've just done. So, HCl. I'm going to snap a proton off of that. That's going to be a Cl minus. So, acid, base. HF. I take a proton off of that. So I've got my acid as HF and my base as F minus. I have an I minus. No proton anywhere. So I need to put a proton back on it to make it HI. This is a base. This is the acid because I added the H plus to it. I have an NO3 minus. Again, negative charge. So I add that proton back, which gives me the acid of HNO3. Here I have an NH4 plus. It's positive. So I need to take that proton off to give me NH3. So conjugate acid, base. I have an OH minus here. Since it has a negative charge, I'm going to add a proton to it to make H2O. So base, acid. And NH3 has no charge, so I'm going to add a proton to it to become NH4. Okay? So there are a lot of things that I look at with this. A lot of it has to do with the charges that I'm looking at, because I know if it's negative, then the proton's already come off. I know if it's positive, there's already been one put on, and that gives me a lot of information about what I need to do. Okay? Questions? So, when we talk about our conjugate acid-base pairs, which we've now learned about, so I have this acid, it donates a proton, it becomes a conjugate base. Great, awesome. That conjugate base is weak if it was a strong acid. If it was a weak acid, then its conjugate is strong. Okay? So there's an inverse relationship between the two of them. Now, H0 plus is the strongest acid that can exist. All stronger acids will donate that proton to water to make H3O plus. So that's why we say that H3O plus is the strongest acid that can exist in water. The OH minus is the strongest base that can exist in water. All strong bases react with water to produce an OH minus. Okay. So that's just to help us rank things. Because of course we always have to rank things. So again, some more practice in identifying the conjugates. Now, I can do some of the identification of the conjugates without really worrying about which is stronger. I know that HCN is going to take off a proton and it's going to be a CN minus. I know that this NH2COH plus is going to take off the H plus. It's then going to be an NH2CO. And this C6H7O6, because it's negative, I need to add a proton to that to give C6H7O6H. And again, I put that H out on the end because that's where the negative sign was. So I'm emphasizing that there, that was the acidic proton by not putting it with the H's in here. So I can do that. Which is stronger, that I'm going to have to get some information about. So where would I get that information? Well, I would look at my exam handouts. So what I'm going to do is pull up my exam handouts and pull this over here, and pull this over here. We're going to go see if we can find like HCN in it. So I'm going to look at my weak acid table and see if I can find HCN. Do I see that in there? No, I don't. Do I see it in my strong acid list? Back here on page 8. I don't. So what I can tell from that, because I can't find it anywhere, is that it's not a strong acid. I know that because it's not in that list, meaning it must have been a weak acid. If it was a weak acid, then the stronger thing is the conjugate, CN minus. Okay, and again, that's because it was a weak acid. Now I can go look, and I always want to look for the thing that doesn't have, when we talk about the HC, the acids, we always want to look for the thing that has the H on it. When we talk about the bases, we want to look for the thing that doesn't have the H on it to try and find it. So I'm going to look to see if I can find the NH2CO. Now, I know it's not in this list right here, so my guess is that it's weak. But I just like to look to see if I can find it. And I don't see it. So given that it's not in that strong table, it is weak, and therefore the stronger component of these two is the NH2COH plus. And what we mean by that stronger component is it's the one that's more likely to react with something, whether that be water or something else. Okay, so it's the thing that is the most reactive in that beaker.
So
Yeah.
the question wasn't which is stronger among them three, was stronger between compound and a conjugate.
Correct. That was what that
Okay.
question was about.
Okay.
Yes. I didn't tell you to rank them. So if I want you to compare the ones that are there, that would be a ranking question. Now, this C6H7O6, since I added a proton to it, that would be an acid that I'm looking for. I know that that is not in my strong acid list, but let's pull up that list again just to make sure. And it is not. Yay, awesome. So that means that this component right here, C6H7O6 minus, is the thing that's more likely to act. And what it's going to do is yank that proton off of water and generate a whole bunch of OH minus. Okay, so that's why it's important that we understand which of these is the more reactive, because when it does what it does and it pulls that proton off, that has an effect on our pH. We then generate OH minus, our pH goes up. When we have this CN minus, that's the most active of these things, is going to pull off a proton as well and raise our pH. And when we have our NH2COH plus, that's going to donate that proton, and therefore our H3O plus is going to go up and our pH will go down. So all of these things will have effects on our pH based on what they are. Okay, whether it's an acid or its conjugate, one of them is going to act. Okay. So let's talk about HF. If I take an H off of that, I end up with an F minus. HF, strong acid? Nope.
Weak.
It's a weak acid. And because it's a weak acid, the stronger component is the F minus. So any F minus that is present will pull a proton off of water. NH4 plus will lose a proton to become NH3. NH3 is not a strong base, and therefore we will get that NH4 plus, if it exists, donating that proton. So, and if it donates, then the pH will go down. C6H5COO. Well, when I put a proton on that, I end up with C6H5COOH. So I put that proton again at the very end where that negative charge was. And the stronger component out of those two, because this is a weak acid, is going to be that C6H5COO minus. And I feel like I'm beating a dead horse by saying this, but it's important that we remember that if that is the stronger component, it will react with the water that's around to change that pH.
Can you
questions about
explain the C6H2O6? I guess I'm kind of confused about why it turns into like C6H7O6H. Like why do we add
it's
another
not
H?
it's not a 7, it's a 5.
Oh, I mean like up there, like on the first
This one?
table. It's a 7.
So
Yeah.
C6H7O6 with a negative charge on it will become C6H7O6 with a proton. And it's because it had that negative charge. I have to put the proton back because I know it's been taken off. That's how it ended up as a negative charge.
Wait, so why did the H2 turn into H7? Wait, is that a 2? Like,
No, it says
that a 2?
C6H7O6.
Right.
And then this is C6H7O6H. So all I
Oh
did
my
was
gosh,
add
wait, yeah, I'm blind. I did that to
I just added the
myself.
one
I'm sorry.
proton. No, it's okay. Not a big
Yeah,
deal.
that makes sense.
Yeah. Okay. So again, the thing that really shifts between Chem 110 and 111 is when we considered things in Chem 110, we considered only that particular reaction that we wanted to think about. Now we have to remember that these things don't happen in isolation. So anything that's going on may have effects on other stuff that's in that beaker. So we have to start thinking about that. And that's what this is really about, is talking about what is this thing, the presence of this thing, how is that going to affect what you're looking at? Because it may not be that this is a strong acid. It's not really, but it still is. An acid, that is. It's still an acid. And so it will affect that pH. Okay. Question so far? Okay. One of the things that they love to talk about is, hey, based on this scale, what's the strongest acid? Hey, based on this scale, what's the weakest acid? That kind of thing. So I mentioned this because I know that there's one of these on the final. I personally think these are stupid, but that's beside the point. That's just my opinion. We need to be able to use this scale to determine which is the stronger acid. Okay. So I know that anything that's above water is a stronger acid than H2O. Okay, so anything that's above this H3O plus is a stronger acid. So if it's up at that top of the table, it's a strong acid. As we go down, those are the weaker acids. Okay, Now, when you see this on a test, it won't have this strong acids part labeled over here. So anything that's at the top of this table is a stronger acid than anything that's below it. So if you're asked to compare HF and CH3COOH, okay, so this guy right here and the one below it, HF is a stronger acid because it's higher in the scale. So that's all you would be doing, is looking for where is it in that scale. So that's your acid side. We have our strong stuff at the top. The base side is reversed. So you have your stronger bases at the bottom of the table. Yep. And then we go up to not as good a base. Okay. So the base is the conjugate of whatever's on the other side. So since HCl is a strong acid, Cl minus will not pick up an H plus to go backwards. It doesn't happen. So that is a negligible activity acid. Negligible activity base, sorry. I apologize. Does that make sense?
Yes.
So you may get thrown one of these and asked to pick which is a stronger acid, which is a stronger base, that kind of thing. We won't ask you to compare across the unless we're talking about this acid right here and its conjugate. We won't ask about like an acid and some other conjugate. That's not a kosher question at this point. Okay? So, looking at what this might look like, which is the stronger acid? H3PO4 or H2S? Well, I'm going to find H3PO4, which is right here, and H2S. Since H3PO4 is above it, I would select this one. When we're talking about NH4 plus and H2O, I'm looking to see where NH4 plus is. Where is my NH4 plus? There. Oh, right there. So right here, and that is below or above the H2O. So therefore NH4 plus is a better acid than that one. When we talk about HCl and H3O plus, HCl is above, so HCl is the better acid. We know that it's going to donate its proton to make that H3O plus. Which is a stronger base. We have OH minus and NH3 minus, or NH3, sorry. There's no minus there. So there's an OH minus here, and where is NH3? NH3 is above it. So OH minus is the better base because it's below. F minus, or HPO4 2 minus. Now F minus is here, and H2PO4 minus is above it. Oh, now where's the 2 minus? That's not the right one. There we go. HPO4 2 minus is below it. So that's the better base because it's below it. CH3COOH is right here. And then we got to find that HS in comparison to it. And HS is down here, a couple down, so that's below it, and therefore a better base. Okay? So again, just comparing where they are on the scale. Questions? Now, I keep saying H plus, and I hope you understand that when we talk about H plus, it's not a real species. What always happens is that H plus gets latched onto an H2O and makes an H3O plus. It is extreme laziness on the part of a chemist to only say the H plus. That's true. But we consider them exactly the same. Okay, so in my mind, there is no difference between them. But from a technical standpoint, it's always H3O plus. Okay. So just wanted to make sure I mentioned that because that is definitely true. Okay. questions on that? Now, auto-ionization of water. Water is a great molecule. Absolutely great. It has so many weird and unique properties, and those properties are why we are able to exist on the planet the way that we do. So water is important. I often write water as HOH, and that's to emphasize that it is an acid with the H part at the front and a base with the OH at the back part. Okay, so it can act as both an acid and a base. It is amphoteric because of that. That means it can act as an acid or a base. And it's amphiprotic, okay, meaning that it can either accept or donate a proton. So that's another term that gets applied to. When water donates a proton to become OH minus, it acts as an acid. That OH minus can act as a base. It is the conjugate base. H2O can also accept a proton, and in that case is acting as a base, which then has a conjugate acid of H3O plus. And of course, we can write this as H2O plus H2O goes to OH minus plus H3O plus, which then gives us that Kw that we talked about, okay? Which has a value at 25 degrees C of 1.0 times 10 minus 14. Okay. So this is my equilibrium constant for water. That's why it's listed as Kw. So all this is products over reactants for this reaction. This is included because they're both aqueous. This is not because both of these are water. Okay. So that's where our Kw comes from and that relationship between the two of them. And pH is a short way for us to report H3O plus, because when we're typically talking about concentrations of something times 10 to the minus 14th times 10 to the minus whatever, we don't want to have to deal with it. So we wanted a better way to deal with it. Now, if a solution is neutral and the H plus equals the OH minus, the pH is 7. If the solution is acidic, the H plus is higher than the OH minus, that pH is less than 7. And if a solution is basic, the H plus is less than the OH minus, and the pH is greater than 7. And that's because we take that Kw expression and we take the negative log of both sides of it. So we take it of this entire expression. And so we get a pKw, because p means the negative log of whatever, is equal to the negative log of the H3O plus the negative log of the OH minus. Because once we take the log, we have to add those things together because they were multiplied before. And of course, the negative log of the H3O plus is the pH, and the negative log of the OH minus is the POH. And of course, if we take the negative log of the value of Kw, that gives me 14. So that's where we get this relationship that pH plus POH is equal to 14 at room temperature. So all of that works together in terms of how we define these things. And it all comes from that K value that we have. So questions about that? It is important that you understand the pH scale. Most of you are in here for some reason to do with medical, okay? pH is extremely important when we talk about medical stuff because a change in a pH of 0.1 is actually a 100-fold change in the concentration of H3O plus. So that's a big deal. And lots of things get messed up if that happens. All right, so that's why we spend some time talking about this. So our POH scale is the inverse of that. So if you want to emphasize the OH side as opposed to the H3O plus side, we talk about the POH scale. So again, it's the negative log of the OH minus, The solution is neutral. They're equal to each other. pOH is equal to 7. The solution is acidic. H plus is greater than OH minus. The pH is less than 7 and the pOH is greater than 7. Solution is basic. H plus is less than OH minus. pH is greater than 7 and the pOH is less than 7. Okay. And if we take the negative log of both sides, we get that pH plus pOH is equal to 14, because I can't say it too many times. We usually measure pH using pH paper, indicators, pH meters. Indicators are things that change color depending on what the pH is, okay? And that's related to the K for the acid-base system of that particular compound. So as it goes from its acidic form to its basic form, it changes color. So we have to start that titration before, or that change after we look at what's going on with our acid bases, okay? So questions about our pH scale or pOH scale. They are inverse from each other. So if the pH is low, the pOH should be high. Now let me remind you of the fun box. Now, this is, as you can see, on your exam handouts. Now, the reason that this is here is to remind you how to get from one to the other. Okay, so if I'm here in the pH and I want to get to H plus, I can see that that H plus is equal to 10 to the negative pH. So that's the mathematical relationship that I need to be able to calculate H3O plus from pH. Okay, direction of the arrow tells me that that's the one that I'm doing. So all of those equations are available to you. The expectation is that you will be able to calculate the other three if I give you one. I will tell you that the expectation is also that you can do this pretty quickly. Because once you've got one of those values in your calculator, doing the other manipulations is not as complicated as it might be. So that takes a little practice. Right? Because I may ask you, hey, what's the concentration of H3O plus for this solution based on the ice table that we're going to solve for this? And now that you have the H3O plus, what's the pH, what's the pOH, and what's the OH minus? So that is a very valid thing for me to do on a test. Questions about that? Now, when we talk about our strong acids and bases, the ones that are listed in this table right here, in solution, they go forward. And we've already said that we know what the concentration of the ions is once this happens. And we often talk about acids in this generic format, where we have HA plus H2O goes to H3O plus A minus. All that means is that there's an anion associated with that proton. Doesn't matter what the anion is. So it could be Cl, it could be HF, it could be I, it could be, it could be any number of things. It could be CH3COO. As long as it has a single positive charge, that's going to be a relationship that we can look at. And for strong acids, the H3O plus will be equal to the concentration of that acid that we put in there. For strong bases, the OH minus will be the same as the concentration of the base that I put in, as long as there's only one OH. If there are two of them, then it will be twice that, which we've already talked about. Okay? So for strong components, we already have a good feel for what those concentrations are going to be. Now, one of the things that comes out of this, let me see if I'm going to get to, I should. So strong acids and bases is completely ionized. So we know that means that there's no HCl or NaOH left in the solution. Since there's none left, that means all of it has become the ions, the H plus and Cl minus, or the NaOH, Na plus and OH minus. So if I have a 0.001 molar solution of HCl, then the H plus and the Cl minus are both 0.001 molar. The same thing will be true with, our OH components. Again, excluding the stoichiometry if there are two of them. All right, so you'll need to be able to find from one of those concentrations, either H plus or OH minus, the pH, the POH, the OH minus, the H3 plus, depending on what you start with. Okay. So, questions on that part? Now, strong acids are molecules where it is favorable to have an anion on its own. All right. The more stable the anion, the stronger the acid. So for that H3O plus is again equal to the concentration of the acid itself. The reaction is complete and it favors products. So if we're talking about a generic HA reacting with H2O to give me an H3O plus an A minus, this reaction only goes that direction. The arrow is one-headed because it only goes that way. Okay. For weak acid, that is not true. It will go both directions. And one of the things that I want to mention, and I may get to it at some point, I don't know, but I need to mention this. So if I were to write a K for this strong acid, that K is equal to the products, that H3O plus, because it's aqueous, times the concentration of the A minus, which is aqueous, over the concentration of the HA. Now, that's always true when we're talking about an acid. Okay, it does not matter what kind of acid we're talking about. That's what a K will look like for it. But if your HA concentration is 0, this mathematical expression is undefined. That's what happens when you divide by 0. And that's why you will never see a value for K for a strong acid. Look one up because they don't exist. All right. So it's important that you understand that strong acids will not have a K value that you can find. Right? Uh-oh, sorry. Sorry about that. Come on. There you go. And if it's not strong, it is weak, and we will have a K expression like this that we can work with. Well, so far. So again, what is the pH of a 0.0235 molar HCl solution? So if I want to find pH, I need to find the H3O plus. The H3O plus is based on this concentration right here. So it's 0.0235 molar because I know that HCl is a strong acid. So I know what that concentration is. There are two ways that I can find the OH minus concentration. I can take 1 times 10 to the minus 14th divided by that 0.0235. That's one way. Or I can take 10 to the negative POH. They will give me the same value, all right? Especially if you use all of the numbers that are left on your calculator. If I want to get to the H3O plus for that particular compound, I need to put in its concentration, 0.0235. Oh, I didn't want to do that, sorry. I have to take the negative log of that value, 0.0235. I don't have to close the parentheses, I just need to hit enter. And that gives me 1.628. Now, one thing, the number that I put in had 3 significant digits. 3 sig figs. When I go from that 3 sig figs into the logarithm, then that logarithm should have 1 less significant digit. So we get 1 when we come out of the log, we lose 1 when we go to the log. So I don't typically test you on that, but that is something that you should be aware of, because you'll notice that that's how I report things. So 1.6 is how I would report this, because that's only 2 sig figs. Okay. So if that's my pH, then I can take in my calculator and do 14 minus that lovely number. And that gives me my pOH equal to 12.4. And again, if I want that OH minus, I can either do the division or I can take 10 to the negative. And of course, on my calculator, it's much easier for me to do second 10x negative answer to get that answer. Okay, so I don't have to type in a whole bunch of other stuff. And so this would be 4.26, because 3 sig figs coming back out of it, times 10 to the minus 13th. And again, that is molar, but we don't typically worry about it when we talk about these things. So cool with that. It's important that you try this a couple of times on your own calculators just to make sure that you're getting the same values, because if you're not, it's typically because of the way you've entered those numbers. So if you're having problems with that, then we should talk about it. Okay, I don't want you to not get the points just because you didn't put them in the calculator right. Now, a solution is created by measuring 3.60. Oh, go ahead.
I was just wondering, so is it okay if we like simplify while we're doing the equations? Because that's what I've been doing. Like, instead of like the copying like the 12.37 and all that, I just put like the 12.4.
If you do that, you will not end up with the same number that I did, because what you're doing is rounding as you go, and the direction that we were given is not to round until the end. I round when I report because that's appropriate, but I should use all of the numbers when I do the calculations.
Okay. Okay.
What you'll see
So
if
how
you
did
do
you do
it.
that thing where you copied it? Oh, sorry. I was just wondering how you copied it.
So on my calculator, all I have to do is hit the up button and then hit enter. It depends on what age your calculator is, whether it will do it or not. So this is supposed to be TI-84 plus with CE, and my TI-84 that doesn't have CE won't do it.
Right.
So some calculators can, some can't. And what you'll find if you don't put all of it, yeah, sure. What you'll find if you don't put all of it in is that you'll end up with rounding errors. And so you'll end up with an answer that's different than mine, which means that I have to go figure out what you did and how you did it and all the rest of it. So that puts me in a not such a great mood. So try not to do that. Sorry. Okay. Any other questions about that? Okay. A solution is created by measuring 3.60 times 10 to the minus 3 moles of NaOH and 5.95 times 10 to the minus 4th moles of HCl into a container, and then water is added until the final volume is 1 liter. What are the H plus and OH minus? What is the pH and what is the pOH? So the first question I would have to ask myself is, how do I attack this? do I just take the number of moles of NaOH, divide that by the volume to get the molarity, and then take the negative log of that to get the H plus and the OH minus? I mean, that's a strategy, but does that strategy make sense to you?
I guess not really, because you have an acid and a base present.
Correct. So what's going to happen?
I guess you need to figure out what's the limiting reactant
So,
here.
yes. Oh, I hate it when this happens. So I'm going to take
Okay.
that NaOH and that HCl. They're going to go into solution, and I'm going to make an NaCl and an H2O, right? And I have information about the NaOH, which is that I have 3.60 times 10 to the minus 3 moles. And my HCl is 5.95 times 10 to the minus 4th. And again, that's in moles. And what I need to know is which is the limiting reagent. Well, since it's a one-to-one relationship, I can say that it's probably HCl, and I'm going to have excess NaOH left over because the mole ratio, I have less of this than I have of this, right? So based on that, I should only be able to make this much product from our limiting reagent calculations. Okay? But what that also means is that all of this amount of HCl will react with the excess of NaOH, and I'll have excess OH minus that's left. Since this is in moles, I can do the subtraction directly. So I can take 3.60 times 10 to the minus 3 moles and subtract the 5.95 times 10 to the minus 4th moles. Again, because all of this, the 5.95 is going to react with this NaOH, and so that's going to go away. So what I will have left is the difference between the two of them. So if I do that happy math, I end up with this lovely number right here, 0.003005. Okay? And so that's the number of moles of OH minus I still have. Now, divide that by the volume, because when I do calculations for pH and pOH, they have to be in molarity. They cannot be moles. They have to be molarity. Now, in this case, that's no different because it's a 1 liter solution. So I end up with this 0.00305 molar. That's a big M, it just doesn't look like it. OH minus. And so I can take the negative log of that number, and that will be equal to my pOH. So again, on my calculator, negative log. Well, I hit that, and I hit enter, and that gives me 2.52. And of course, it should be 2.5. So that's my pOH. pH is equal to 14 minus the 2.5. And no, I cannot do that math in my own head because it's not exact, but that's okay. I'm just that bad. And that's 11.47, which I'm going to round to 11.5. Right, so that's 2 of those. I already know what the concentration of the OH minus is. I had already solved for that right here. So this right here is the OH minus concentration. And so if I want that H3O plus, I need to take 10 to the negative pH, which is equal to 10 to the negative 11.5. And so I can go second 10x negative. And that gives me 3.33 times 10 to the minus 12. Thank you. Okay. So remember to think about what's in your beaker. Are you going to have any chemistry that goes on before you have to do these calculations? It's important that we take that into our account when we're looking at these things. Does that make sense?
Kind of.
It will make more sense because we're going to be talking a lot more about these kinds of things. So I think it will get better as we do more.
I guess my question is about the OH minus remaining, and it's like, so you subtracted from whatever initially you had just to kind of see how much you got left, and then
Yes,
you find the molarity based on that number, right?
that's correct. That's exactly what I did. And that's because it's a one-to-one relationship between the two of them. So that's why I would do it that way.
Are we reporting like the H plus and the OH negative in like two different formats? What is so the OH negative is moles over liter?
So in this point, yes, I did. Moles over liter is still molarity. I just have different units listed. So I wrote one out and I have M for the other one. That's all. Since moles per liter means molarity, it doesn't matter which one you actually report.
Okay.
Okay. Okay. So I wanted you to take a minute and do one set of calculations similar to what we just did. I want you to walk through. I'm going to give you 2 minutes to do that. We'll see how far you get. And then I'll present these answers so that we can make sure that we're on the same page for at least some of them. Okay. Okay. So when I get presented with a problem like this, I look at it and I say, all right, I have 6.50 times 10 to the minus third molar KOH. That tells me what my OH minus concentration is. Because it's a one-to-one relationship, I know that that OH minus is then going to be 6.50 times 10 to the minus third molar. That's my starting place. I can find the negative log of that to take the POH sorry to put in the wrong number. And that gives me 2.187, yada, yada, yada. Again, I want 2 sig figs when I do this, so I want 2.2 as my POH. If I then want the pH is equal to 14 minus that 2.2, which no, I can't do that in my head, so
1.8.
but
11.8.
oh, 11.8. Yes, you got there much faster than I did. My subtraction and division skills are lacking. We don't do that as much of them, so 11.8 there. And of course, we need the same decimal number of decimal places because I did a subtraction. So if I then want to go to the H plus, I take 10 to the negative pH. Or I can take 1 times 10 minus 14th divided by the OH minus concentration. Either one works. And that gives me 1.54 times 10 to the minus 12. So again, anything that's reported as molarity would have 3 sig figs. Anything that's reported as pH or POH has 2. And again, I'm not going to test you on that, but I like to harp on it because I just want you to remember that. It's because of the mathematics that we've gone through. So cool with that. Okay. Now a solution is made by measuring 4.62 times 10 to the minus 2 moles of HBr and 5.83 times 10 to the minus 4th moles of RBOH into a container, and then water is added to a final volume of 2 liters. What are the H plus and OH minus, pH, and POH? So again, I have an HBr that reacts with my RBOH. Balanced chemical equation then gives me RBBr plus H2. Oh, so taking my cation here, putting it with the anion there, cation here, anion there, gives me the RB and the H2O. Wrote them in the other order, but there you go. Now, if I know that this concentration here is 4.62 times 10 to the minus 2 moles, and this one is 5.83 times 10 to the minus 4th moles, I can see that this one is bigger than this one. Therefore, all of my OH will go away. I will have H plus left over. Finding how much I have, I take my 4.62 times 10 to the minus 2 moles minus the 5.83 times 10 to the minus 4th moles. And that will give me some kind of number that I can work with.
So, and it depends on what gets used, then you will have that concentration on, because in the previous reaction, we used up all the H plus, and in this one you
Correct.
use up all the OH.
Correct.
Okay,
So we have to see which one's left over. That is correct. And if I'd entered it correctly, then I wouldn't have had this problem. My calculator does not always love me. Correct. So I have to look and see which one is going to be left over, because if I have, a complete reaction so that everything's used up, then I know that there's no excess I need to worry about in my pH 7. It's whatever's in excess that's going to change those values. I end up with 0.045617 moles, which technically should be 0.0456. I would cut off the 17 because I only had 3 sig figs. So if I were reporting that at that point, that's what I should report. And that is moles of H plus that are left over. Now I'm in moles. I have to get to molarity. Because this is not in a 1 liter solution, I have to divide by the volume that it has, which is 2 liters. So I have to divide this thing by 2 to make sure that I know what that concentration is. So that's the concentration that I have that I need to work with. And that's my H plus. If I want to go from H plus to pH, it's the negative log of that value. So I would take the negative log, that answer. That gives me 1.64, which I'm going to report as 1.6. POH is equal to 14 minus the 1.6, which, if I'm not mistaken, is 12.4. But I'm going to do it on here just because I want to make sure I have all of those numbers to work with to go to the next calculation. So it rounds to 12.4. That is correct. But now that I have that value, which is my POH, my OH minus concentration can be taken as 10 to the negative 12.4, which I'm all those decimals for. So that's why I do that. And that gives me this number, which is 4.38 times 10 to the minus 13th. So again, 3 sig figs there for that. Okay. So questions about what I did or why I did it?
It makes more sense now. Okay.
I was hoping it would, and don't worry, we will end up doing more of these when we get to the buffer section. So, all right, let me take a look and see what's on my next slide. I'm pretty sure we're going to quit here. Yeah, questions? Any questions? What I will say at this point is that there are a bunch of sample questions at the end of this. What I think would be appropriate at this point is to send you guys off to try and do these on your own. And I will walk through them at the beginning of class next time so that we can make sure that we've had a real conversation about what those answers are and how I walked through them. Sound okay?
Yes, ma'am.
Okay, awesome. If anybody has any questions, you can feel free to hang out and I will deal with them. Otherwise, have an excellent weekend. Thank you very much for being here, and I'll see you later.
Thank you.
Thanks.
Have a good weekend.
Bye.
You too. Bye.
Bye.
Bye.